This is video 2 for symmetries in music and mathematics. We'll now be talking about Cayley's theorem. Cayley's theorem says, assume G is a group. Let the function G going to sim G be the function defined by f of G times H, which equals G times H. Then F is a monomorphism and G is isomorphic to a subgroup of sim G. So we have to define what G is. So G is going to represent all the integers, Z. So if we were to associate that with the keyboard, and C would be our identity, so 0, which is the identity in Z, and C. So we can go all the way up the scale, all the way up the piano, up into infinity, and the same going down the opposite direction, just as integers do. We can now set a group of pitch classes. So if we were to essentially take the large group and compress it down to 12 notes, C, C sharp, D, E flat, E, F, F sharp, G, A flat, A, B flat, B, you have our 12 notes. So this in mathematics will represent Z divided by 12, which is going to represent our G. We now go to permutations. So now what we've done essentially is every note in Z divided by 12, or our group G, every note represents a permutation. So C, or phi sub 0, is going to represent the movement from 0 to 0, 1 to 1, 2 to 2. So essentially, each permutation, each note in the group represents a permutation. So C, or phi sub 0, will represent the movement from C to C. Okay? And so now we know that is the identity because there's no movement from C to C. And so that also means that we would move from C sharp, if we were to start on C sharp, and also move to C sharp. And the same for D, D would move to D, E flat would move to E flat, all the way up to B. As another example, if we were to have the permutation C sharp, or phi sub 1, this permutation would represent a half step. A half step is described as moving from one note to the very next note, or before or after it, okay? Half notes make up the chromatic scale, of course. So C sharp permutation would represent the movement from C to C sharp. If we were to use an example in this permutation, for example, E, if we were to select E, the permutation C sharp would represent E moving to F. Okay, if we were to do another example, say the permutation described by F sharp. F sharp would represent, if we were to start with the identity C, it would represent the movement from C to F sharp. Okay, so using another example with this permutation, if we were to select the note F, F sharp permutation would represent movement from F to B. Okay, in music, this permutation represents a tritone. A tritone is an interval that is made up of 3 whole steps. Another example is the permutation A flat, or phi sub 8. So, going back to the piano, if we were to start at the note C, our movement based on this permutation would be from C to A flat. Using the same permutation, using another example note, if we were to start on G, our movement based on this permutation would represent G moving to E flat. And in music, this permutation represents a minor 6. This is described as a half step down from the major 6. And so each, as I said before, each note in the pitch class represents a permutation, all the way starting from C all the way to B. So there essentially are 12 permutations that we can have based off of Cayley's theorem. And so what do we do with permutations? We create composition tables. So going back, referring to the website, you can see the composition table listed out. And one of the benefits that can be used with this composition table would be if we were to essentially need to transpose, for example, the trumpet's note C is different than the saxophone's note C. And so we would need to transpose so that everyone would be on the same accord. So you'd be able to use an example like this to give a permutation so that the trumpet and the saxophone and the piano could all be playing the same note.